So my talk today is about how you can use your data to give your customers superpowers. My name's Kirsten Westeinde, and I work at Shopify. I'm going to give a quick background about what Shopify is so that you can understand where I'm drawing the examples that I use in my presentation today from. Shopify is a leading cloud-based commerce platform, and it allows merchants to sell across multiple channels. So these channels include everything from Pinterest to online stores to physical retail locations. And our merchants include everyone from tiny mom and pop shops all the way up to massive brands. And we are hiring, so if I didn't get a chance to talk to you upstairs in the speed networking, please come find me afterwards or check out our careers page. So I'm a software developer. I do backend mostly, and I recently started working on a large-scale machine learning project. So I didn't have any formal training on machine learning, and thus I had to quickly bootstrap my skills to become effective. And it turns out that it wasn't as scary or as complicated as I thought that it would be. At a very high level, there's 4 steps to a machine learning project. You first have to identify the problem that you're solving. Secondly, you want to frame it in such a way that it looks like a machine learning model. Third, you want to train your model. And then lastly, you need to productionize it. And then you're done. Obviously, there's a little bit more to it than that, so I'm going to dive into each step a little bit more. The first being identifying a problem. There are some problems that are inherently good candidates to use machine learning to solve. And if you use machine learning to solve them, it will result in a really elegant solution and quite accurate as well. But if you try to use machine learning on a problem that is not a good candidate problem, it's going to result in a lot of pain and suffering. I know this from personal experience. And also the result is not going to be any better than what you could accomplish with a rules-based system. So since machine learning and artificial intelligence are such hot topics these days, I've seen people trying to use it to solve every problem they encounter. So it has become almost like the hammer in the famous saying, when you have a hammer, everything looks like a nail. So I'm going to try and help you identify how to find the nails in this example before using the hammer on them. Okay, so what are these unicorn problems that machine learning is really good at solving? Before I can answer that question, I need to go through some definitions. So by a show of hands, how many of you would be able to tell me what the difference is between supervised learning and unsupervised learning? Okay, cool. And then what about the difference between classification and regression? Okay, so we're sitting around 50% of people. I will still give the answers so that we're all on the same page before diving in. So supervised learning is when the correct answer is given, and we use these answers to predict the answer on future data points. An example of this might be if you're given a data set about how much money each of your customers spends on your site, and it's broken down by gender, country, and age. So then you create a model, and then you see a new customer coming to your site who is a 30-year-old female from Canada. So now the model has to predict how much money that person is going to spend on your site. And so this correct answers come in the form of a labeled training set. So labeled just means that the correct answer is applied to each example. Unsupervised learning problems are when you're given an unlabeled data set and the model has to find some structure in it. So an example of this might be, given all of your customer demographic information, can you find groups among which your product is popular? The majority of machine learning problems, or products I should say, that we interact with these days tend to be supervised learning problems. So I'm going to focus on them for the rest of the talk, but I should note that a lot of these problems start off with an unsupervised phase in which we learn features on an unlabeled data set. Okay, so then there's 2 general types of supervised learning problems, which are classification and regression. And the difference between the two is what the output is. So classification, the output, is a discrete value. So these are yes or no questions, or selecting between a predefined set of answers. Regression is a prediction that can be any continuous value. So an example of this might be if you're trying to predict a housing price. It can fall anywhere on this continuous value scale. If you can frame your problem as a classification or regression problem with consistent input features, then it's a very good candidate to solve with machine learning. But not all problems will appear to be classification or regression problems right away. Sometimes it takes some massaging to see how they are so. An example is recommender systems. Let's assume that I'm trying to recommend for a Shopify merchant an app from our app store that they should install on their store. I'm not classifying anything, really. The outputs are not predefined, and the output should be an app, which is not a continuous value. So I might conclude that this would not be a good problem to solve using machine learning. But we all know that recommender sisters are a common application of machine learning, so what gives? Well, if you think about the problem in a slightly different way, it can appear to be a regression problem. So what if for any given merchant, I applied a score to every app in the App Store about how effective it would be on their shop? This score is that continuous valued prediction in the regression problem. And now it's a simple task of just selecting the app with the highest score. I'm going to go through some examples of problems that we use machine learning at Shopify to solve. These were super complex problems, and machine learning was the key that we needed to unlock our ability to offer a lot of these features. It allows us to make predictions with extremely high accuracy and speed. So I hope that as I go through these examples, it inspires you to think about some problems at your organization that you could use to use machine learning to solve. The first example is order fraud detection. So this is a supervised classification problem. We were given a data set of a bunch of historical orders, and we knew the output of whether or not they were fraudulent. So we trained our model on this data set, and now it gives an output, which is either a yes or no answer for every new order we see. This answer tells our merchants whether or not they should feel confident fulfilling the order. So we did previously have a rules-based implementation, but our new machine learning implementation is hugely more accurate. And this saves our merchants a lot of pain and money, and then it also builds increased trust in our platform. The second example is about Shopify Capital, which is a product that offers loans to merchants on our platform. So it's basically like microloans for entrepreneurs. It's a supervised regression problem where we try and figure out the probability that they'll be able to pay us back in a reasonable amount of time. And offering these entrepreneurs money can mean the making or the breaking of their business, and we would not have been able to offer this product without machine learning. And the final example I'll use is classifying our merchants by industry. This allows us to give industry-specific success metrics, as well as a customized experience to our merchants depending on which industry they fall in. And this is because someone selling ebooks, for example, has a very different requirement from our system than someone who sells shoes. And machine learning allowed us to unlock this customization. So at this point, we've identified the problem that we want to solve. We've ensured that it is actually a good problem to use machine learning on. So now we need to frame it as a machine learning model. Before we start using an algorithm, it is very important that you have a good understanding of your problem domain. You may have heard a story shared by the data science consultant, Martin Goodson, which talks about a machine learning project that was commissioned by a hospital to classify pneumonia patients between those at high risk and those at low risk. The goal was to save the hospital some money by sending home the patients who were at low risk with antibiotics and checking in the patients who were at high risk. But the team of data scientists didn't have access to all the information that they needed to solve this problem. This is because the data set was inherently flawed. It turns out that patients who came to the hospital with pneumonia who also had asthma were always immediately sent to intensive care because it was such a dangerous condition to be associated with it. And then while they got to intensive care, they got extremely good care and didn't have any complications. So the machine learning model was able to make very accurate predictions on the data set it was given, but it predicted every time to send home patients who had asthma, which was obviously not the right call. So this is just an example of why you need to understand the problem domain before you start using an algorithm to solve it. So either you should read up on it yourself, or you should include someone who's a subject matter expert on your team. So a machine learning algorithm needs 4 things. It needs a prediction target, it needs labeled data, it needs features, and it needs an acceptance criteria. A prediction target is the thing that your model is trying to predict for each data point. It needs to be a very clear definition, and it will likely be domain specific. And it has to be understood by your product team as well as your development team. Some problems this is easier for than others. So for example, if we're talking about predicting housing pricing, we know that it just means the financial amount that a house is worth. But we might want to take care to specify that it's in US dollars and it's a pre-tax amount. This was slightly harder for our fraud detection example because we weren't exactly sure what should be included of this bubble of fraudulent orders that we were calling. So we did a lot of research to set in stone this definition, and it was hugely beneficial to us before tackling the problem. So ideally, your prediction target should be codified and unit tested. This will ensure that it's not susceptible to mistaken changes down the line, and it also gives the whole team consistent outputs and a way to validate their model changes. So you probably all remember a couple slides ago when I said that supervised machine learning needs to know the correct answer for a bunch of data points. That's your labeled data set. Having a good data set is non-negotiable. Your machine learning model will only be as good as the data that you give it. So what do I mean by a good data set? Well, you want to ensure that your data set has all of the features it will need to make a prediction. This is where having a good understanding of the problem domain comes in. So for example, with the example that I just gave, if there had been someone who understood the domain, they might have included a feature about whether the patient was asthmatic or not. On top of understanding your data, it's important to include data points from a wide variety of situations. So sometimes this can involve manual intervention if you don't have access to this wide variety of situations. An example here that everyone's probably heard of is if you're building a facial recognition algorithm, it's important to include both genders and all of the races in your training set for it to be able to make predictions properly. The more data that you have access to, the better. And this is not because you need millions of data points for your training set, but rather because the more data you have likely means the more variety of situations it encapsulates, and you can inspect this data to find these varied situations to include in your training set. So if you don't have any data yet, you have a couple options of how to get started. There are a ton of open source data sets available, put out by companies like Amazon and Google, as well as the government and various academic institutions. Some of these might work for your problem. But if they don't, then you have to go out and collect the data yourself. This might seem like a daunting task, but think of it as a long-term investment in the future, because you never know what other problems that you'll be able to use this data for. If you're having difficulty collecting the volume of data that you need, you can try something called artificial data synthesis. Now, it's not going to work for all problems, but it might just work for yours. So what this basically does is it takes an existing labeled data point, and it adds a small amount of distortion to it, such that we have a new example, but we know the outcome still. So, for example, if you're doing text recognition, and one of your training points is a picture of the letter X, we can then create a new training point, which is the same image, but just slightly more blurred. Or we could create another one that is the same image with the X slightly farther to the left, and so on. Once you've collected your unlabeled data set, now you have to label it. So this specifically means applying your prediction target that you've defined to each data point. If you've managed to come up with a codified definition for your prediction target, you may be able to do this programmatically. Otherwise, there are some other options other than doing it manually yourself. So you can actually crowdsource data labeling, which is pretty cool. I found a marketplace called Amazon Mechanical Turk where you can hire people to classify your data for you, and there might be other examples of this as well. Okay, so after all of this, we have our labeled data set. Well, there's one final step before we can start training our model, and that is the data pre-processing. So this just ensures that the data is fed in the correct way to the model. There's a bunch of different things you can do depending on your data set, but one pretty common practice is called data normalization. So this ensures that the values for all of your features fall within the same scale. So for example, if you have one feature that is equal to age and one that's equal to salary, if we're talking about humans, the age probably falls within 0 to 100. And let's just say that the salaries fall within 0 to 500,000. If you input this data in this format, it's possible that the massive values for the salary feature will drown out the impact of the age feature. So what we can do is replace our salary feature with the feature that's equal to salary divided by 5,000. This way, its values will fall between 0 and 100, but we'll also still get the differences across the data points, and they will shine through and allow us to make accurate predictions. So now we're ready to figure out what our features should be. Our features are like the inputs to the machine learning model. So they should be the collection of all of the information that you need to make a prediction. So a good mental check to see if you have a complete feature set is give a human expert the value for each feature for one data point, and given that, they should be able to confidently predict the outcome. You can use a combination of intuition and statistical analysis for this. So for example, in the example that I gave of Shopify Capital lending money to merchants, my intuition tells me that the amount of money they make on our platform per month would be a good feature. But statistical analysis might tell me that the age of the merchant also impacts whether or not they pay us back. At the end of the day, machine learning is just statistical analysis, so it's only going to get the correct answer if it has access to all of the data it needs to do so. It can't use any higher level knowledge to solve these problems. So we humans know that Christmas falls in December, and thus we're likely to see an increased volume of sales in the days leading up to Christmas because it's the holiday season. But a machine learning model can't know this unless we explicitly tell it. So having a feature that's equal to the current month isn't good enough. We also need an additional feature that tells us whether or not it is the holiday season or not. So as you're selecting your features, something you should be thinking about is what point in my system is this model going to be making its prediction? You obviously can only use features that you have access to at the point where you need to make the prediction. Often you're going to need to do some transformations or aggregations on the production data so that it's in the format that you need for your model. For example, the number of sales in the last month is probably the format that I would want the feature for the Shopify Capital example. So this would mean a query to the database that aggregates the number of orders for a given shop ID and whose created at timestamp is between now and 30 days ago. It's also important to ensure the quality of your feature data. So some things you should be asking yourself are, who's producing it? Is it possible that they might change its output or meaning at some point? Will they be producing it forever? How often is it blank? Is it in a consistent format? You want to make sure that it's consistently produced across all surfaces in all different situations. At Shopify, we have orders coming in from our web applications as well as our iOS and Android mobile applications. And they don't share 100% of the same attributes. So if I selected a feature that was only present on mobile orders, it would introduce bias into my algorithm. Feature selection is not something that you can just do once and then forget about it, unfortunately. The data available to you, as well as the real-world features affecting the outcome of your problem, are constantly changing. It's a good practice to reevaluate your features often, as well as their impact on the problem. My team is consistently doing statistical analysis and experimentation with our features to ensure that we always have the most up-to-date and the most impactful data being fed into our models. And finally, your model needs an acceptance criteria, which essentially dictates when your model is good enough. This is going to be very different depending on the problem that you're solving. So in the examples that we heard earlier this morning about art, perhaps a lower accuracy is acceptable, whereas in a lot of healthcare applications, a lower accuracy is obviously not acceptable because it's human lives that we're talking about. A good example of this is that less than 1% of orders that come into Shopify are fraudulent. So if we just said that it wasn't fraudulent every time, we would have a higher than 99% accuracy, which would normally be considered pretty good, but obviously it's not good enough in this situation. So something that can be really helpful to do is to split your predictions into 4 categories: the true positives, the false positives, the true negatives, and the false negatives. And it's up to you to evaluate what these mean in your specific problem domain, because there's always going to be a trade-off between the 4. So you have to determine what the impact of that trade-off will be. In production machine learning systems, though, accuracy is not the only acceptance criteria. You'll also likely need to care about how fast your model can make a prediction in, as well as how many resources it uses to do so. Coming up with this criteria should be a shared exercise across the product and development teams. So the third step is to train your model. I'm going to be intentionally only touching on this at a very high level for a couple of reasons. The first being that I only have 30 minutes to talk to you all, and I could give a more than 30-minute talk on this topic alone. But it also is the most well-documented step, and there are libraries that you can use straight out of the box for this. So it's sometimes okay to treat this as a black box when you're getting started and then dig into it a little bit more later. I will go through a very, very oversimplified example, though, so that we know what the inputs are and the outputs are and how they fit into the overall process. So training a machine learning model is an iterative process wherein we make a guess, we calculate the error associated with that guess, and then we make another guess that moves in the direction of minimizing error. We do this over and over and over again until we have reached the minimum error guess. Training is complete once we have found that point. So it can be helpful to think of this as a 2D example, because that's what our brains are good at wrapping themselves around. But in this 2D example, the machine learning model would be the line of best fit. The things that we're guessing are the weights that we apply to our features. So if we remember back to grade 9 math, the equation of a line is y equals mx plus b. So we're trying to guess the m and the b here, and the x is the input data point, and the y is the prediction that we make on it. So there's entire university courses taught on this subject. I think some of you have taken them. So I obviously covered it in like 15 seconds, but if you want to read more, these are some like keywords, courses, and frameworks that are really great to follow up on. I'd also be happy to chat after this if anyone has any more questions or would like these resources again. Okay, so the final step is productionizing your model. This is where things get really interesting, and in my opinion, where machine learning solutions still have the farthest to go. So far, everything that I've talked about has been completely implementation agnostic. But from here on out, I'm going to start talking about some examples of how we did things at Shopify, and this will include implementation details. But the ideas hold true regardless of how you choose to implement it. So at Shopify, all of our data lives in a data warehouse, and we use PySpark to access and transform this data. So that's the Python API for Apache Spark. Having a Python API for it is great for us because our team is already familiar with it, and it also allows us to hire people that are already familiar with it. Spark is a very powerful engine for large-scale data processing. So at a high level, we have two use cases for serving up our predictions in production. The difference between the two is how we need to access the prediction data. So the first class of examples is push-based data. So we run a job that creates all of these predictions, and then we push them. And only once the merchants are logged in and engaged with our platform will we display it to them. So these are things that don't have time sensitivity, because the difference in time between when they're produced and when they're consumed could be a lot. An example of this would be a suggestion to install an app. But others are needed in a pull-based fashion at runtime. So the example here is the order fraud detection. We need to know right away after an order is placed if it is fraudulent or not. So in both cases, our models are trained and tested using PySpark. But the difference comes in how we serve up the predictions. So in the first case, the push-based case, what we do is we run a batch job that comes up with a bunch of predictions and emits them as Kafka events. These Kafka events contain all of the information needed about this prediction to be able to execute it. Then our Ruby on Rails code consumes this Kafka event and does whatever transformations needed to serve it up to our merchants. In the second case, though, where we need predictions at runtime, we actually load our completely trained model into our Ruby environment and deploy it with our system. We do this using something called PMML. So that stands for Predictive Model Markup Language. It's a standardized language for expressing model definitions. You can kind of think of it like an XML for machine learning models. And that model is actually deployed with our code and makes predictions at runtime for us. One of the downsides about this approach is that every time we make a change to the model, we have to manually re-include it and redeploy it. So it's not too manual. We have jobs and everything to do it, but it does require intervention. OK, so you don't want to train your model and then release it into the wild right away. You want to do some verification that your model is accurate enough, fast enough, and whatever other acceptance criteria that you've defined. You want to do this by mimicking running your model in the scenario that it will actually be running in. So the first step is to test it against a test set. So this is a labeled data set, but it was not included in your training data set. It can also be helpful to follow one specific example whose outcome you know through each step of the model and ensure that nothing looks amiss. It is also a good practice to explicitly test your model for bias. So to do this, you can expect segments of data and ensure that the accuracy is the same across each segment. So back to our order fraud example, I might look at orders by geography, or I might look at orders that came from our mobile applications versus web applications. And you want to ensure that the accuracy is the same across each segment. So if you're serving up real-time predictions in the way that I described before, where you actually load your model into production, something that you can do here is deploy your model into production, but don't have it actually serving up its predictions yet. So it's not going to be interrupting any user flows, but it will be making these predictions in the background. And this will allow you to compare the prediction that was made against the actual outcome of what happens. So you can do this through a reconciliation job. There's also another benefit of this, which is that it starts to give you some production statistics around performance, so speed and resources. But this obviously doesn't make sense for a recommender system. Because if you don't make the recommendation, then the action's not going to happen, and you can't compare what you thought would happen against what actually happens. So for this, if it's the first time deploying your model, doing verification against a test set and inspecting examples is perhaps the best that you can do. But what you can do afterwards is every time you update your model, you can compare the output of that model with the previous model on a given data set. It's possible that the values will have changed depending on what changes you're making to your model. And this is where you need to understand the problem domain to ensure that these changes are valid. But you can verify that the results fall within a similar distribution. So once you have accurate enough predictions in a fast enough time, you're ready to go live. You can either choose to deploy it to 100% of your users right away or deploy it using A/B tests, depending on how your organization releases new features. After you deploy it, you still want to maintain visibility into every prediction that is being made. And this should include some monitoring as well as alerting if the performance ever drops. Because we have deployed these models into the real world, and the real world changes at a fast pace, we're going to have to update our model as circumstances change, and we should be programmatically alerted when this happens. So for example, if I had a model 20 years ago that was trying to determine the success of an advertising campaign, I might have only cared about how many cities that I posted my billboard in. Whereas today, this has obviously changed a lot, and you might care about things like whether you posted it on Facebook or Instagram, and if you use a carousel ad versus a single product. So this verification and deployment process that I've described applies not only to the first time that you release your model, but also to every subsequent update that you make to it. My team trains our models and releases a new version every single day. So we've done as much as possible to automate and streamline this process. As you're building out the pipeline for your first machine learning problem at your organization, you should be taking explicit care to make it reusable. This way, when you go to solve your second problem, 80% of the work is already done for you, and you can only focus on the details of the problem at hand. So at Shopify, we're moving towards using TensorFlow. TensorFlow is developed by Google, it's open source, and it has a super low barrier to entry. So if anyone's looking to get their hands dirty and get a model running up and running quickly, I'd suggest trying this out. The benefits for us are that we can train it and then deploy it in Google Kubernetes engine, which is where our production code lives. It will allow us to serve up predictions in real time, but it will also standardize the two areas that I've talked about, which were the push-based and the pull-based. They'll both be using the same methodology now. And for our push-based predictions, switching to real time is going to be hugely beneficial because, like I mentioned, there can be a time delay between when we create the prediction and when we serve it up. And so this means that it's possible that this prediction has become stale or is no longer the best prediction by the time that we go to serve it. So we have a lot of checks and balances in place to ensure that it is still valid. And the second that we have live model predictions, then we can delete all of this code, and that will be amazing. So I really hope that I have managed to drive the point home that you need to have a good understanding of your problem domain. More often than not, when machine learning projects fail, it's not due to bad code or bad math, but it's due to a lack of understanding of the problem domain and the data set and features that you're working with. So you should either be making yourself a subject matter expert on the topic or else including one on your project team as a stakeholder. I also hope that I have made it clear that there's much more to production machine learning products than just training a model. Everything from data collection to testing your production target to releasing your model in production will be the responsibility of the project team. And having a strong foundation in software concepts will be hugely beneficial for you. You also need to be curious about your problem and have a willingness to experiment. I can almost guarantee the first model that you come up with will be terrible. I know ours were. So it's important that you view this as a learning opportunity and not a failure, and continue to iterate until you come to the correct solution. You don't need a degree in statistics or formal data science, but that does help if you have it, to get started. Many examples of the complex problems that we've used at Shopify, that we've used machine learning at Shopify to solve have been gone over. And I also hope that you've been able to see the massive impact it's had on our merchants' lives. I hope this has inspired you to think about problems you could solve at your organization, and that you start using your data to give your customers superpowers. Thank you.